Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 20th, 2025, which means this paper arrived just yesterday. The big hook is a physics-focused benchmark and evaluation that reveals most image editors still fail at realism, with scores under 60 on physical effects. The paper is titled, PICABench, How Far Are We from Physically Realistic Image Editing? And the implications for model training are quite significant. Beyond the benchmark, the authors introduce a region-grounded judge, show strong human correlation up to 0.95, and report video-based training gains of 1.71%, with consistency rising from 24.57 to 25.23 decibels. Alright, Figure 1 shows why semantic success still falls short, because the edits often break physics. The panels group failures into 3 dimensions: optics with mismatched shadows or reflections, mechanics with impossible support or deformation, and state transition, which means changing material or environment states like season or temperature. Each row contrasts instruction alignment with visual inconsistencies. The takeaway is that realistic lighting, contact, and state changes remain fragile across common edits. Figure 1 showed where physics breaks in edits. Figure 2 presents the dataset statistics that make those checks measurable. Panel A allocates question pairs across 8 subdimensions, with global state transition taking the largest share. Panel B plots instruction lengths for 3 prompt levels, which confirms that explicit prompts are much longer. Panel C summarizes the composition across optics, mechanics, and state transition, so coverage stays balanced. So Figure 2 summarized coverage. Figure 3 presents illustrative examples that put those physics checks into context. The grid shows 8 subdimensions, with each panel pairing an edit instruction and region-grounded questions. Region of interest boxes, which are highlighted areas used to focus evaluation, anchor the yes or no checks so the judge assesses the right evidence. This design reduces hallucination and makes failures interpretable across optics, mechanics, and state transitions. Alright, Figure 4 lays out the end-to-end pipeline that powers the physics-aware benchmark and its judge. The top row handles data collection and instruction design. The middle row covers region of interest and question annotation. The bottom row runs evaluation with a vision language model that focuses on the marked regions, which reduces hallucination. The flow is modular, so each step can be improved independently. With the pipeline established, Table 1 reports head-to-head results on the physics benchmark. It shows accuracy and consistency in decibels across 8 subdimensions. Accuracy is the percent of region-grounded questions answered correctly, while consistency tracks similarity in non-edited regions, so unchanged content stays intact. Closed systems lead with about 62% overall accuracy, and open models cluster below 60%. Optics looks stronger than mechanics and local state transition. Fine-tuning with video-derived data lifts the Flux 1 context baseline by about 1.7%. Consistency also improves by around 0.7 decibels. So the core message is clear. Today's image editors satisfy instructions yet miss physics, with overall accuracy barely above 60%. Region-grounded judging and physics-focused subdimensions expose these gaps, and video-derived supervision nudges models forward. The implication is practical. Train with physical priors and evaluate locally. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.